take a look at this question here. This is what we're going to be working through today. So two thin circular discs of mass m and 4m, having radii of a and 2a respectively, are rigidly fixed by a massless rigid rod of length L equals square root of 24a through their centres. This assembly is laid on a firm and flat surface and set rolling without slipping on the surface so that the angular speed about the axis of the rod is omega. The angular momentum of the entire assembly about the point O is L. Which of the following statements are true? This is a question from the 2016 JEE Advanced Exam, Paper 2. Now this is an exam that Indian high school students would sit if they're wanting to get into an engineering university. Now this question was the most requested one for me to go over, and it's definitely extremely difficult. I think this question is maybe intended to really sort out who are the top students taking this exam, and many students may try to skip over this one. It's from the physics section. Now physics is my area of specialty, so I was quite interested to take a look at this. Note that in this video I take a lot longer than the probably recommended 3 minutes per question to solve this particular one. Some of that's because I'm explaining it as I go, but it actually is a really difficult question and would take me, I think, a lot longer than 3 minutes to solve it, especially in an exam situation. So it is very hard, but with that being said, I think that you can get through it, and I hope that this video maybe makes it a little bit clearer for you. I'm going to start by adding anything to the diagram that we currently know or that we can easily find out, maybe through a bit of trigonometry. So we can assign this angle in here to be theta, and we will be able to find sine theta and cosine theta by enlarging this triangle here in the corner. Finding sine and cosine of theta will help us out later on. A, L, this angle is theta, and in this triangle this is the hypotenuse, so by Pythagoras you can work it out to be the square root of L squared plus A squared. So to find cosine of theta, we have the adjacent side and the hypotenuse. Cosine of theta is L over square root L squared plus A squared. From the question we know that L is equal to the square root of 24 times A, so we can substitute that into our equation for cosine of theta. When you complete the algebra, that works out to be the square root of 24 over 5. Likewise, sine theta will be using the opposite side and the hypotenuse, and it will be A over square root L squared plus A squared. And when you substitute in the value for L here, we end up with this being 1 over 5. Let's also extend some of the lines on our diagram. I'm extending this line out a bit, and the reason for that is to mark the direction of the angular velocity vector when it is spinning around its own axis. Now the angular velocity vector you can find using your right hand and wrapping your fingers around in the direction of motion, and the thumb will point in the direction of that vector. This is one of the right hand rules of physics, and if we're spinning that way, then this is going to be our vector pointing out this way. Now that's not the only axis of rotation that we're dealing with in this problem. These wheels are also moving around the origin, and so we want to mark that angular velocity vector as well. So if we're rotating like this, we've sort of got our fingers on a diagonal and wrapping them around in that motion. Our angular velocity vector is actually going to stick up a little bit, and I'll draw it on here. This angular velocity vector for the motion of the wheels around the origin is going to be offset from the z-axis by the angle theta, which is the same angle as in here. I'm going to mark that vector as being omega. What we're also going to want to do here before we really get started is to find the location of the center of mass of this whole assembly. We've got a pretty big mass here, 4m, and a smaller mass here, so the center of mass will be somewhere in between the two. But let's work out exactly where it is. Now there is a formula to find the location of a center of mass. Call that COM, and you can find that by taking the m1 x1 plus m2 x2 over m1 plus m2. Now m1 and m2 are just our two respective masses. x1 and x2 are the location of these two masses from the origin, and that's all we're going to need to do. So let's put the numbers into there. m1 will be m, its distance along this axis is going to be L. We're going to add that to 4m, which is our second mass here, times its distance, which is 2L. That's all going to be over m plus 4m, 5m. Simplifying the algebra on this, and we're going to end up with 9/5 L. Drawing my L's a little bit inconsistently, I'll make them nice and curly again. Okay, so at 9/5 L along this bar is going to be our center of mass. Well, 1L will be 5/5, so add another 4/5 along here is going to be our center of mass. So I'll mark that there, center of mass. And to just make it nice and clear again, when we're talking about this angular velocity vector here, we want to know how far it is from the horizontal axis, and that angle in there is going to be theta because these two angles are opposite each other. The last thing I want to do before we really get started in answering the question is to write down 3 more formulae, which are reasonably simple but will become very useful in answering the question. The first is that angular speed is related to tangential speed or linear speed, and the radius by v over r. Just know that every point on a rotating object will have the same angular speed, but the tangential speed will differ depending on the radius of that point. Now we also want to know something about angular momentum, and if we have that denoted by L, it is going to be equal to the moment of inertia times the angular velocity. Just to refresh your memory, the moment of inertia of a point mass is mr squared, where this is the mass on a certain radius of rotation. And for a disk, the moment of inertia is mr squared over 2, where r is the radius of the spinning disk. First, we want to look at checking out the claims made in part A of the question, that the center of mass of the assembly rotates around the z-axis with an angular speed of omega over 5. Now let's see if there's any truth to that. So let's pick a point to study, and we are going to choose the center of this first disk, that point right in the middle there, and we want to find out its linear velocity, how it's moving through space. We already know its angular velocity is little omega, and we can use our trusty formula that we just spoke about to find its linear velocity too. So let's have a look at that. We can find its linear velocity, v, from r omega. In this case, if we treat the bottom point where it makes contact with the floor to be stationary, then that center point is rotating at a radius of a, so we can set its radius to be a, and therefore its linear speed to be a omega. That linear speed is going to define how quickly that point can move around in space, around the origin. So we can now use that to work out the magnitude of the angular velocity vector about the origin. That capital omega will be the linear speed divided by the radius, which is now the radius of going around O, not just little radius a. And that's going to be our linear speed we just found, a omega over r, which is going to be L in this case, the distance from the origin to the point that we're talking about, L. So that's all good. We've found the angular velocity around O, but what the question was actually asking us was to find the angular velocity around Z. So what we found is actually a little bit offset from what we're trying to find, and it's offset by an amount theta. So if you know your trigonometry, and I can draw the triangle again quickly here, if this is theta, if this is our Z axis, and this is our value we've just found, then since we have an adjacent side and a hypotenuse, these two values can be related by Z is equal to omega times cosine theta. We know from what we worked out at the very start that cosine theta is square root 24 over 5. So if we put all our values in, we have a omega over L times square root of 24 over 5. If we then also substitute the value of L, which we know to be square root of 24a, we get a omega and if we cancel out some of the terms, we can get rid of these, we are left with omega over 5. And that, ladies and gentlemen, means that part A of our exam question, that the angular speed around the z-axis is omega over 5, is actually true. So A is one of the correct answers to this question. Let's now look at part B, and we want to see if the magnitude of the angular momentum of the center of mass of the assembly about the point O is this value, 81 ma squared omega. Okay, so let's see if there's any truth to that. So what are we going to use for this? It's our trusty formula here, that our angular momentum can be found by multiplying together our angular velocity and moment of inertia. Now for around the point O, we already know what our angular velocity is going to be, and all we need to know is find our moment of inertia. Because we have a center of mass on a massless rod rotating around that point, we can treat it as a point mass, and this here, mr squared, is the formula for the moment of inertia that we're going to use. Our angular momentum around the capital omega axis, denote that like that, is going to be equal to our moment of inertia there, which is our mass. Now what's our mass? It's going to be the center of mass, and center of mass means you can treat all of the mass of the assembly as being at that point. So it's going to be m plus 4m. It's going to be 5m rotating at a distance of 9/5 L, because that was the location to our center of mass. So we're going to have that's the moment of inertia times our angular velocity, which we worked out in the previous part to be a omega over L. Nearly made a fatal flaw, but don't forget to square the radius there. mr squared omega. We're going to end up with 5m 81 over 25 L squared. We can substitute L with its known value, and what we end up after doing that and simplifying is 81 over 5 square root 24 a squared omega m. So let's go and have a look at what the question was asking. The question claimed that it was 81 m a squared omega, which is actually pretty close because we had an 81, but it's not exactly the right answer. So for part B, I would say no, that is not a correct possible answer. You'll give it to them though, they do try to trick you. If you'd been rushing through this and seen that there was an 81, you might be like, yeah, this is pretty close, might go for it. But yeah, pretty nasty there, trying to trick you into giving one wrong answer. Let's check out part C now, and that's wanting us to find the magnitude of angular momentum of the assembly about its center of mass. So no longer about the point O, but around the axis that it's rotating on. It claims that this value is going to be 17 ma squared omega over 2. So let's see if that's another lie or if that is true. In the previous part, we found the angular momentum along this axis and I called it L capital omega. This time we're being asked to find the angular momentum along this axis here, and I'll call that L with a little omega. The direction of these quantities again comes from that right hand rule. We are rotating like this on this axis, so our angular momentum vector points down in this direction. This time, to find the moment of inertia along this axis, we have two disks rotating on their axis, so we're going to use this formula here, that the inertia for a disk is mr squared over 2. Working this out on paper, we have L little omega is going to be the inertia of the first disk plus the moment of inertia of the second disk, all times omega. So inertia of the first disk is going to be m times the radius that it's rotating on, which is going to be a squared over 2. Add that to 4m times its radius, which is 2a all squared, that over 2. That's our moment of inertia terms, and timesing that by omega. Working through a little bit of the algebra here. And we're going to end up with 17 over 2 ma squared omega. Does that check out with the question paper? Very nice to see that actually yes it does. This is the same value here, so another possible correct answer. I guess it sucks if you quit at question A thinking you got the only correct answer, because, well, there was a second one waiting for you, and we haven't even tested question D yet, so let's see if that's right or wrong. Question D is asking us to find the magnitude of the z component of the total angular momentum. It claims that it's 55 ma squared omega. What we've done in the previous two parts of this question was find two different components of the total angular momentum. Now, both of these previous values for the angular momentum on each axis are on diagonals, so they have components along the vertical and horizontal axes. So we just want to find the component of this angular momentum, which is in the vertical direction, and it looks like we're going to be subtracting the component of this, which is in the vertical direction, because this one is pointing downwards and this one is pointing upwards. From similar trigonometry that we've already been using today, to convert this value into its vertical component, you will take this and times it by cosine of theta. And because you might be able to see this one is in the opposite direction, we have an opposite and a hypotenuse. To find the z component here, we will take this value, L, and times it by sine of theta. So our Lz component is going to be L capital omega times cosine theta. Subtract from that L little omega times sine of theta. This was our answer to B, so we can substitute that in here, that 81 over 5 square root 24 a squared omega m, times it by cosine of theta, which we found out right at the start, square root 24 over 5. Subtract from that the answer to part C, which was 17 over 2 ma squared omega, times it by sine of theta, which we also found out at the start, 1/5. Now we're just going to do a little bit of algebra here, try to simplify this as much as possible. Now this to me seems like really ghastly algebra to try and simplify this down without a calculator, which I believe you're not allowed in the exam. I don't know, I guess we can keep going doing more and more algebra to try and get these numbers here to simplify out to something and compare it to the value of 55, which is what is claimed in the question paper. Me, being a lazy little person, have glanced at this on a calculator to see that these numbers come out to be about 76 times ma squared omega, which is not equal to our proposed value of 55. So I'm going to say that's a wrong answer, but very big congratulations to anyone who follows that through just by pen and paper. In fact, congratulations to anyone who attempted this question and got to any point along the way. It's really, it's a very advanced question. To have this in an exam, it requires lots of different steps of thinking, and I think this is a really impressive exam question. In my last video, when I reviewed the first paper from the 2016 JEE exam, I didn't realize that there was a second paper that also had to be solved on the same day with very little break. So knowing that makes me respect people who have sat this exam even more, because that's very difficult to sit two exams, so close to each other on the same day. Thanks for watching this video, and please subscribe to my channel if you'd like to see more videos like this. And a very big good luck to anybody who is currently studying for exams.